Hello everyone, and welcome to another edition of the SOLIDWORKS Simulation Step-Up Series. My name's Omar Zoni, and today we're going to be discussing basic failure analysis inside of SOLIDWORKS Simulation. We're going to start with a little bit of presentation, and we're going to move back and forth between presentation and software. That being said, thanks for joining, and let's go ahead and get started.
Okay, so today's topic is going to be basic failure analysis inside of SOLIDWORKS Simulation. Let's begin with a basic definition of failure and how we define failure in parts and assembly. Typically, we say failure is a permanent change in the part that could be size, shape, or material properties that result in the design no longer being capable of performing its desired task. So these are some pretty obvious examples of failures inside of parts. So you can see the arrows kind of calling out sections in the part that have failed. Inside of SOLIDWORKS Simulation, there are many different ways to account for this type of failure, specifically for the onset of failure. In this particular step-up series section, we're really going to focus in on single static overload failure. So we're not going to be doing fatigue, creep, or other failure mechanisms. Now those are available inside of SOLIDWORKS Simulation and they'll be touched on in future sections, just not today. So before starting FEA, it's very important to interpret exactly how the failure occurred, or interpreting failure basically. And there are lots of different things to consider. The most common thing to consider, though, is really what does the deformed shape look like, because the deformed shape can really unlock a lot about exactly how the part has failed. So, typically that allows us to interpret whether it was a ductile failure or a brittle failure. There are also things like, were there abnormal conditions, maybe in a corrosive or an extreme environment. Looking at things like, were there other parts that also failed? Did it occur after significant life, indicating maybe like a high cycle fatigue? But the most important thing to identify, and really what's vital for us to continue in FEA, is to figure out exactly what the cause and mechanism of the failure was. Now, another thing that's also very important is for us to try and understand the allowable limits for our parts. So so we can establish basically a design life. It's as scary as it is to contemplate. Even parts associated, critical parts associated in the airline industry have a design life associated with them. So if we exceed the design life under standard loading, we can be pretty sure that the failure is going to occur. And really by understanding the allowable limits really allow us to come up with factors of safety, right? Because we want to know, what is the stress that we're looking for, the stress or displacement that we're looking for, or temperature. There are so many different criteria that we could potentially be looking for, but assessing those limits really allows us to come up with what our factor of safety is. And our factor of safety basically correlates the actual response with the allowable response, right? So, and we're looking for factors of safeties that are greater than 1. So now let's talk a little bit about static failure inside of SOLIDWORKS Simulation. So again, we're going to be really focusing on static linear analysis and kind of static overloading, right? So, and we'll walk through these steps in more details once we get into the software, but there are many ways that we can evaluate whether or not your design is going to be overloaded and potentially fail. The first is by, and the first thing, kind of a more manual approach, is by looking at things like stress plots and looking for high stress regions. So, here's kind of the basic steps that are required. I'm assuming here that you guys are already comfortable with SOLIDWORKS Simulation. You guys know how to set up and run an analysis, create meshes, define material properties. We're not going to, that's not the intent of this. We really want to kind of dive into failure. So again, this kind of walks through the steps required to generate a stress plot. You can see all the different stress criteria that are available depending on whether you're looking at brittle or ductile failure, or even inside of ductile failure or brittle failure, there are different criteria that call for you to use different stress values. So whether it's a von Mises stress or a shear stress or a principal stress, combination of principal stresses, there are different stress criteria that are available. So that's, kind of allows you to do a stress plot. You can probe results, you can list results. You can also do factor of safety plots. And that's kind of where we're going to spend the majority of our time today, because we really want to kind of dive into the different factor of safety plots that are available. The different ductile and brittle material, or ductile or brittle failure theories that are available, and when these different ones are appropriate. So just be aware that if you're creating factor of safety plots inside of SOLIDWORKS, that you need to have the requisite material properties defined, and that can either be the yield or ultimate strength depending on the criteria that you're using. If not, you'll get a warning here, and there are ways that you can actually manually enter criteria into the factor of safety plot definition, so if they're not defined in the material properties. And here are kind of some of the steps required. And again, don't get caught up here in kind of these images, because we're going to walk through setting this up inside a SOLIDWORKS simulation. But here are kind of the steps required to set up or create a factor of safety plot, right? So we call out we want a factor of safety plot. We pick our criteria. We pick what our allowable, kind of our stress limit is, and then we generate our contour plots. So when we talk about ductile or brittle failure, I think it's a little bit important to it's important to understand exactly what we mean. So ductile materials basically they're capable of taking a permanent set, or when they yield, they get some permanent deformation. Examples of that are things like steel or aluminum, some plastic, some copper. Although there are classes of each of those materials that behave brittly, and there are conditions where they'll behave brittly also. When we talk about brittle materials, generally what we mean is they're characterized by the fractures taking place suddenly without any real significant yielding. So usually these materials exhibit higher strength and compression as opposed to tension. So if you look at the material properties, you'll see a higher ultimate compression strength as opposed to ultimate tensile. And normally, typical materials are things like cast iron or ceramic. They're probably the two most common. Now, ductility it's not really a property that you enter. You don't go into material properties and say, hey, I'm going to turn ductility on. It's really a characteristic of the material, right? And depending on the stress strain curve, kind of how it behaves post yield, between yielding and ultimate failure, that kind of defines whether or not a material is brittle or behaving brittly or ductilely. Now, when we're talking about brittle material behavior, typically the things that we look for is, if you're looking at a material spec sheet, you're looking for a percent elongation that's less than or equal to 5. You're looking, again, for tensile strengths that are ultimate tensile strengths that are much, much lower than ultimate compressive strengths. A lot of times brittle materials won't enter a yield strength. If they do, the yield strength and the ultimate tensile are going to be very, very close to each other. And really the key way to figure out if it's a ductile or brittle failure is examine the failed parts. Now when we talk about ductility, just to add kind of complexity to the problem, ductility can really be affected by a whole host of things. So the three kind of more common are temperature. So just think about how materials that you interact with every day behave differently under in a cold environment as opposed to a warm environment. One that jumps off the top of my head is there's a reason why when you put glass in the freezer, right, when you're creating your frosty mugs for drinking grabbing an ice cold beer, there's a reason why very, very cold glass is much, much more prone to break as opposed to glass that's sitting at room temperature, right? The behavior is a little bit different depending on temperature. Now also strain rate, so how quickly you're loading a part can change a material from brittle to ductile or vice versa. If you load things very, very quickly, they're much more likely to behave in a ductile material. And then even material grade, right? So here are a couple different materials where you can see we've got aluminum 7075, aluminum 319. Just based on the grade, we can see here the 7075 behaves more ductilely, elongating 11% before break, whereas 319 behaves much, much more brittly, right? So the manufacturing process for these two aluminums yield it or cause it to behave differently. Same thing for polyethylene, which is a plastic, right? Typical kind of like a tensile bar test. We can see at room temperature we get a nice ductile behaving material. At low temperature behaves much more brittly. Now, what I'd like to do now is kind of hop into the software. So this is the example that we're going to use. It's a real simple robotic actuator example. We've got a couple parts that are going to be interacting with one another. But the takeaway from this, again, I don't want to spend a lot of time kind of walking through setup of the problem. Even the boundary conditions and loadings, not as important for this problem because I really want to get to post-processing and how you would, take advantage or how you would interpret results. Okay, so let's hop into SOLIDWORKS. Here's our model. We've got our finger, which is the part that we're really most interested in. We've got this, what we're calling a jaw bush, which in addition to creating contact here in this slot is also where we're going to be applying a force. And then we've got our kind of the thing that it's grabbing right here. That's also in contact with the finger. So I'm going to skip you know, how you turn on SOLIDWORKS. I'll just point out one thing. You know, for the ductile material, we're going to assume that it's a steel 1020. We can see we've got our yield strength defined. Here's our tensile strength. No tensile ultimate strength, no compressive ultimate strength. There's a great section in the SOLIDWORKS Simulation Step-Up series that's already been done that deals with material property definition. I'd suggest, you know, that there's a lot here in material properties, so, you know, including a relationship with materiality that, you know, what this SS does not mean structural steel or stainless steel. It means there's post-yield stress strain curve defined. So if you want to do a nonlinear analysis, lots of different things available. Now with respect to contact, great series on contact and exactly how you can account for contact in your models. That's already been done. We're assuming that we've got no penetration contact between these two bodies, between the finger and what it's grabbing, and inside of this slot here. So you can kind of see they're highlighted in purple and blue, the faces that are going to be in contact with one another. Now, let me just turn all the restraints on at once. I'm not going to kind of describe all the boundary conditions. Or I'm not going to go into great detail about the boundary conditions, but this guy is basically fixed. The bottom face is constrained. You know, the inside face here is not allowed to move up and down, nor is it allowed to move kind of into the plane, into the screen right now. And this guy is a hinge constraint, so it's basically allowed to rotate about that cylindrical face. And let me just hide those because nobody likes to look at all those the call outs there on the screen. And then with respect to force, very, very simple force applied, just a force on the interior face of this body. You can see it highlighted there in blue, and it's kind of in the X direction, so moving that thing in the X direction. Now, that's the setup. Let me pop back into the PowerPoint presentation and let's talk a little bit. So as I mentioned, we're going to initially look at ductile material, right? That AISI steel 1020. So here are the different ductile failure theories, and I would say that arguably the most commonly used, probably the one that I use 80% of the time if I'm, you know, doing any failure analysis, fatigue, or a factor of safety analysis, is the von Mises stress criteria, also known as the distortion energy theory. Now, very, very simple criteria. It basically says yielding occurs when the stress in your material exceeds the when your analysis basically exceeds the von Mises stress. That's when yielding occurs. Now you've got the maximum normal stress theory. Yielding occurs when the maximum or minimum normal stress exceeds the maximum or the tensile ultimate or tensile or compressive ultimate strengths, depending on whether you're looking at you know, positive principal stresses or negative. And then you've got the maximum shear stress theory that kind of uses Mohr circle to determine what the maximum shear stress is, and says that yielding occurs when the maximum shear stress is greater than half of the yield strength. Now, it's important before we get into this to kind of understand exactly what elastic and plastic response is. So as I mentioned, we are going to be running linear analysis. Now, we don't have to run linear analysis inside of SOLIDWORKS, and again, you know, this there'll be some discussion in future step-up series sessions about exactly nonlinear analysis, but we're doing a linear analysis. And basically, linear analysis is good at predicting the onset of yielding. But if you're looking for results beyond yield, it's not going to be correct. And just real briefly, right, in a linear elastic stress analysis, basically, we make the assumption that the response follows the Hooke's law, basically. So, and the slope of the stress strain curve is basically the modulus of elasticity. Now, if we've exceeded yield, you know, if you think of a common stress strain curve, right, once you exceed yield, it no longer behaves linear. It kind of starts to tail off, right, and the slope of that curve changes. So that's when we have to move to a nonlinear analysis. A nonlinear plastic analysis can accurately predict points beyond yield, all the way up to ultimate, but it's not valid over the ultimate stress, right? Because that's where we expect for fracture to start occurring. The takeaway here, though, another takeaway is that once you've exceeded the limits that are kind of specified in your material properties, that's when your results are going to start degrading, right? So just be aware of that. Now, the von Mises stress theory, we're going to start there. I'll go back into the software in a minute here, but again, yielding occurs when you've exceeded the von Mises stress of the material. Von Mises stress is an equivalent stress state. It's derived from your total stress, so it's basically the sum of, it's basically sigma 1 minus or sigma 3 minus sigma 1 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 2, or whatever the sigma, let's see, it's 3 minus 1, 2 minus 3, 1 minus 2. All of those squared, you take the square root and then divide it by 2. So it's kind of the sum of the roots squared. It's a scalar, unsigned stress quantity. It doesn't have direction. There's no indication of whether or not it's tensile or compressive stresses. Always reported as positive, and it's a good way to correlate you know, a lot of different test data into a more general 3D stress state, the most widely used also. So let me pop back into the software, and what I'm going to do is I'm going to come in here to my stress plot, and I can create a new stress plot. Maybe, you know what, I'll do that. So let's say, look, I want to create a new stress plot. I want you to use the von Mises stress. I'd like for you to report it in megapascals. I'm really only interested in the stress of this finger, so I am going to say I want you to plot this on just this finger. And here are my stress values. Now, you know, there's another really good setting that I purposely didn't set there. So you might see this, right? And you're looking around and you're like, hey, I don't see any red in this. Where exactly does that maximum occur? Well, if we come back here to edit the definition, one of the things that you need to account for is, you know, if you've got a big assembly and you just want to look at stresses in one particular body, there's a nice checkbox here that says, hey, I only want you to show the stress range for this particular part. And now you can see it dropped that from, you know, whatever it was, over 1,000, probably from, you know, a stress singularity to 454. Now, you know, just kind of recalling what we just did in the PowerPoint presentation, remember the factor of safety is kind of the actual stress divided by the allowable, right? So here we've got my actual maximum stress is 454. My yield strength is 351. So let's pull up a calculator. And factor of safety is actually going to be that yield strength, 351 divided by 454. So I would assume that if I did a factor of safety plot looked at von Mises stress criteria, I would expect the minimum factor of safety to be about 0.77. So let's go ahead and do that. I'm going to say, hey, look, I want to create a factor of safety plot. I'm going to do selected bodies again, just pick that the job. Kind of the finger, say that I want to use the von Mises stress criteria. I also like to do this. So I like to say, hey, look, I want you to set the maximum, the upper limit for factor of safety to 10. Anything above 10 is going to show as color blue, basically. Now it's going to ask me, hey, when you're doing this, you know, I'm picking the von Mises stress criteria, but do you want me to compare that to the yield strength or the ultimate strength? For a ductile material, if you're using the von Mises stress, it's kind of always compared to yield, but this is a place where you could change it. You could pick the ultimate, or you could do a user defined. And I will just say OK, and now we can see and just as we suspected, right, from our real simple calculation, 0.77 is my minimum factor of safety. We can see where it occurs. And again, anything 10 or above is just going to show up in blue. So you can see most of this part is probably designed quite well, but we might want to thicken this up if we, you know, if we want to. We want a factor of safety that's above 1, right? So that is our kind of our factor of safety for if we look at von Mises stress. Now, another ductile failure theory is the maximum normal stress. And, you know, maximum normal stress, it kind of requires us to go back to kind of strength of materials, or our first kind of structural analysis class. Remember Moore's theory, or Moore's circle, basically tells us there are 3 mutually perpendicular planes passing through any point in a body such that the stresses are purely normal to that plane and can be in tension or compressed. So the stresses that occur on that plane are called our principal stresses, P1, P2, and P3. The maximum principal stress is P1. That's going to be the most tensile, the largest, most positive stress. Then you've got your middle principal stress in a 3D analysis, and then your smallest, which is P3, is going to be the smallest, typically the most compressive negative value. Principal stresses have a vector quantities, so they have a direction as well as a sign. Now, let me just kind of pull up. Let me go back to SolidWorks here. If I can figure out how to do that, guys. All right. And I'm not going to create a new plot. I'm just going to go back to my von Mises stress plot, and let me just say, instead of von Mises stress, I'm going to say I want to look at the first principal stress. And if I click that pin right there, it basically allows me to plot things without it you know, going off the screen. So we can see the max of P1 values basically, and I can do that for P2, P3, but let's just say that I want to do P1, and then I'm going to go back to my factor of safety plot and switch it from, you know, being based on the von Mises stress criteria. I'm going to go to maximum normal stress, and we can see that the minimum factor of safety for this case is about 0.61. All right. Now the third criteria is the maximum shear stress theory. And the maximum shear stress theory, again, it requires us to kind of go to a Moore circle, calculate what the maximum shear stress is going to be, the maximum shear stress component basically, and then we can relate that. If that is larger than 1/2 of the yield strength of the material, that's when we know yield is going to start. Now, there are ways for us to go back and look at the different shear states. But remember, these are not going to be correlated to our principal stresses, right? So I can look at shear on any of the planes, but it not quite as easy to correlate. So if you're looking at maximum normal stresses or maximum or the von Mises stress criteria, those are kind of easy to correlate in your head, but the maximum shear stress is definitely not, right? So if I come in here and say I want to go to a maximum shear stress, which is also known as the Tresca theory, here is my factor of safety plot. So all kind of look the same, all are calling out the same problem areas, but you know, all have a little bit different value. So it's important to figure out exactly what criteria that you're going to use. Now that being said, let me pop back in here and let's just do a little comparison of the theory. So basically these lines represent the onset of yield for the different stress criteria. Now, for ductile stress criteria, remember we had 3. So we had the maximum shear, and you can see the dotted line here. It's kind of hard to see as it comes down here, but it kind of creates this shape right here. Now, the maximum principal stress theory is just this outer box. And then we've got our von Mises stress criteria, and then these black dots represent actual empirical testing. So a couple of things that you should take away. Basically, the maximum normal stress theory is best when P1 and P3 are similar. So if you know, your P1 and P3 values are relatively similar, then you know, this can be an adequate one to use. Von Mises correlates best with the empirical data. So you can see here's what where the empirical data lies. Real close It's real close to our von Mises. And I would say, again, von Mises it is probably one of the primary indicators of when yielding is going to occur in ductile materials. So that's the one that I use probably most often. But just be aware the other ones are out there. There are certain specs that call for utilization of those different theories. And then just to kind of summarize here, and you know, so here are the von Mises and principal stresses, and then here, you know, I want to point out another thing, right? You guys see these are basically the results that we just got, but you can see the values are very different, right? This is telling me that I've got a minimum factor of safety in the maximum normal case of 0.17. Remember, ours were about 0.7, 0.75. Here's our shear stress. Now the reason that is because the minimum is actually occurring on this body. So it's always important to understand how results are calculated, right? In your factor of safety plot, if I just come in here and say, hey, look, instead of just plotting it on this one body, I want you to use all the bodies. look at what that does to my factor of safety. So we can see, right, the minimum factor of safety is not on that the finger, basically. It's on one of the other components. And if we're really only interested in the results in that finger, you got to be careful when you're interpreting results, right? So again, this is not meant to be the simulation step-up series on like looking at results, but just be aware in situations where I'm kind of most interested in looking at an individual part, you know, it's always good to kind of look at the overall stress state and the whole model. But I always like to create kind of displacement, stress plots, factor of safety plots for the specific body that I'm interested in. And, you know, so that's kind of what I do. And if you're looking at stresses even, you can get even more granular where you just plot results on a face or displacements on a face. So there's lots of different ways where you can get much more granular results. Okay, now that being said, let's get back to the PowerPoint here, if I can figure out how to do that. Now let's talk a little bit about brittle failure theories. So with brittle failure theories, we really have two, and one of them is a repeat, right? The maximum normal stress theory. But if we're going to use the maximum normal stress theory with brittle failure analysis, instead of using the yield strength, because yield strength is often not defined in brittle materials, we want to use the ultimate strength of the material. And then there's the Moore column theory, which basically is kind of a combination where you look at P1 over the ultimate strength of the material and tension plus P3 over the ultimate compressive strength, and just be aware that if this is negative, if P3, which is going to be negative, typically is, well, pretty much always, is going to be your smallest, most negative number, that the ultimate compressive strength also needs to be entered as a negative, right? And when these two values are equal to or greater than 1, that's when you're going to have failure. So let me just compare these theories real quickly for you. So again, here is the Moore column theory, kind of follows this path right here. And then here is the maximum normal, right? Looks really the same. And the experimental results tend to indicate that Moore column is going to predict the onset of yielding earlier, right? So, you know, up here it kind of falls right on. Here is an area of concern, right, where the results are kind of a little bit different between the two theories. Always better to use a theory that's going to predict yielding a little bit earlier, right? Because we don't want to be designing to out here and then realize that our yielding occurs here. So Moore column is the one that typically gets used more often. And let me just pop back into SOLIDWORKS, and I have another model set up here. So a second study. All I've done is switch the material properties to gray cast iron, which is a ductile material, behaves ductilely, and not going to walk through looking at the stress results again, but if we come here to factor of safety, I want to point out a couple things. And so, okay, we've got Moore column plotted here, but let me come here to edit definition. I'm going to switch to the maximum normal stress, and I'm going to say on selected bodies, and I'll just pick my body again. And now you can see, I've set this to ultimate, right, which is exactly what we want. If I set it to yield, there's actually no yield strength defined for this material. So when I try to plot this, I'm going to get a warning that says, hey, you asked me to use my stress criterion for this material as yield, but it doesn't exist. So I would have to go back here, go back to ultimate. And here is my stress distribution. So we can see the minimum is about 0.35. And, you know, alternatively, I can come up here and say I want to use the column stress, Moore column, and in that case, it's going to ask me to specify the ultimate tensile strength and the ultimate compressive strength. And you can see, because I either specify those manually or it pulls those directly from the material to property definition. And you can see, let's plot this real quickly. You know, they're both around the same 0.35, 0.39, but remember when we talked about brittle materials, the tensile strength is going to be the ultimate tensile strength is going to be much smaller than the ultimate compressive, which is exactly what we've got here. So let's kind of summarize what we've done here. Again, brittle failure theories. Here's our factor of safety using, again, when these plots were generated, you can see not just plotting the factor of safety in the finger, right? It's plotting it in all the bodies. For more column, it actually looks like the minimum factor of safety is in that finger, but for the maximum normal stress, definitely not. It's in this center cylinder where the force is being applied. So again, be aware, right? If you're only interested in results in that finger, plot the results only in that finger. Now, let's kind of wrap up here. So talk a little bit about correlating the tests and a couple misconceptions. Just testing after analysis doesn't constitute correlation, right? So you could have a situation where your analysis results are interpreted to suggest that a part won't break and it doesn't break. That doesn't necessarily mean that the results are correlated, nor does it if an analysis predicts that a part will break and it breaks at the predicted location. That still doesn't mean that things are correlated. The analysis may be correct, but the results have not been correlated. In order to correlate results, there are a couple things that you really want to do. You probably want to put some strain gauges in the areas that have some gradually changing strain, where you can monitor that strain and then correlate that to the analysis. You're going to want to complete FEA first to kind of align those gauges to the principal stress direction. Another thing that I really like doing is correlation of deflections are a really good way to validate that your boundary conditions and loads and your contact between parts are set up correctly. And the real hard thing when you're trying to correlate to tests is test and analysis procedures must match, and a lot of times they don't. When you're looking at FEA, a lot of times, FEA assumes kind of idealized, perfect conditions, and a lot of times tests don't react. There's no way to mimic that idealized setup, right? So you might have to do some testing to validate your analysis assumptions. Obviously, factor of safety equal to 1 is not a good design point. You want your factor of safeties to be greater than 1. Real world loads can oftentimes behave unexpectedly. And obviously, if you're kind of correlating to tests, you got to make sure that your testing is controlled and very repeatable. So that being said, we're going to wrap up here. I hope you guys found this particular section useful. There'll be a lot more content coming out. I encourage you guys go to the SOLIDWORKS YouTube channel, or do a quick Google search of the SOLIDWORKS Simulation Step-Up Series. We are going to be adding more and more content. Please leave us some feedback, leave us some comments if there are things that you would like to see in future series, in future episodes. We are really loving generating this content, and we're loving the feedback that we're getting. So appreciate it from all of you guys, and thanks for taking a little bit of time out to listen to this. Hope it was useful. Thanks again, guys. Bye.